Well, thank you for the complete and kind introduction. I'm now a little bit nervous. Okay. It's a great pleasure to be here. One of the reasons is I grew up about 200 miles from here, a small town called Duncanville, Texas, outside of Dallas. So, you know, Texas A&M had a big presence in my childhood. Yeah, let me tell you a little bit about the works we have been doing. Actually, we did not coordinate, but Sasha's introduction kind of mimics the first few view graphs, so thank you. And also, I would welcome questions throughout, so please don't be shy to ask if I can clarify anything. So yeah, just a starting point, at least one way to structure things in common language is to remind or think about, let's say, conventional textbook electronic materials, namely thinking about metals with many, many free electrons, typically of order 1 per unit cell, down to insulators where we have no free electrons, and of course semiconductors that have become very, very important, that are quite in this intermediate and tunable regime. So just to remind ourselves that in the early days after the foundations of quantum mechanics, as it was applied then to the periodic discrete translational symmetry of a lattice, an early and important understanding was that if you then map out the electronic structure, namely states of the electrons in energy versus momentum, you could have a very nice and simple way to think about these different states. Namely, if I put my chemical potential here in this gap, I'll have an insulator. If I approach a band edge, I'll have a semiconductor. And if I'm kind of in the middle of a band of states, that I'll have a metal. And so, of course, you know all of this, but it's just to remind ourselves in the context of some of the things we're interested in, is that this is very deeply predicated on the accuracy of an independent electron description. Right? So this is actually not a priori obvious, but this is based on the notion that I can describe these states and these sorts of systems as if the electrons act quite independently of one another, let's say outside of a self-consistent field or that sort of thing. And that's actually quite reasonable for a lot of things. And so, as just introduced, surely this train of thought has been very powerful. I used to walk by this every day from the parking lot, actually, when I was at Bell Labs, to now, you know, your typical chip in your computer has of order a billion transistors. So you know this story, but it's just to emphasize that the fact that one can engineer these sorts of complicated systems is very much reliant, underlying that, on the fact that you can really design the electronic structure and understand what should be a many-body problem in very simple terms. Another stream of thought in this class of materials, let's say in semiconductors, is to say that if you have structures that modulate the electronic structure or the band gap on the typical wavelength associated with the de Broglie wavelength of the electrons, then you can actually start to probe and manifest very interesting quantum properties. This first concept coming out of IBM, Yorktown Heights, in 1970s, really went a long way to this program. And these sorts of concepts and related tunneling, both of electrons and pairs of electrons, was a very important motivator for this whole line of thinking. But despite this, very soon after this discussion of fairly independent electron descriptions being a great triumph of the application of quantum mechanics to solids, it was also quickly realized that actually there are spectacular failures as well. And so let me just try to illustrate that into schematics here. The top part is what we just described, that if I have now an empty band of states, and you start to fill electrons into these states, the fact that I can describe this as shifting a chemical potential in a rigid band is really another way of saying that the electrons are quite weakly interacting at this level. And if I then put the chemical potential such that I have one electron per site in a simple structure, I can fill each site with spin up and spin down, and I should generically have a half-filled band, i.e. a metallic state. So another very broad class of materials are cases where this type of screened phenomenon fails quite spectacularly. And in fact, it's very difficult to draw an appropriate picture for this, but this is an attempt to do so. So if I have cases where I have strong electron correlations in a material, and I start to put electrons in the system, what happens is very different. This, you may say, is more of a schematic of the electron spectral function or something of that order. But the point is that as we approach 1 electron per site, we go to a state that is the very opposite of a band metal. It actually opens up a gap in the electronic spectrum, and it's known as a mod insulator, i.e. a situation arising from the strong electron correlations in this material. So this you can kind of think of a situation where the electrons are so strongly interacting, want to avoid each other, and so they localize one on each site. And so the charge degrees of freedom are largely quenched in this regime. And therefore, the low energy dynamics is dominated by magnetism, right? So if I just show you, if I have 2 sites, I have an electron here and an electron here, the remaining degree of freedom, maybe are they going to have any preference in their spin? Right? And it turns out that you can intuitively imagine that if I have antiferromagnetic alignment, I have access to virtual fluctuations, right? I don't violate Pauli exclusion. I would have a problem here. And so a lot of these so-called mod insulators are one-for-one associated with antiferromagnetic order. And so maybe somewhere in some class you've heard this statement that magnetism is really a quantum mechanical manifestation of these sorts of Coulomb repulsions, and this is a classic example. The point of this discussion is to say that the electronic structure in these kinds of systems is quite a bit different. It is not really a rigid single particle band, but the structure itself evolves on very large energy scales. So here I slide in 2 different labels, and indeed we can find experimental or materials examples of these 2. And to give you a sense of the types of things that my community is interested in, is to say, can we, in broad strokes, take the program that I illustrated in semiconductors or conventional systems and try to make heterostructures, interfaces, and devices, but using materials where their electronic structure is much more manifesting these sorts of electronic interactions. So this is a picture of a cross-sectional electron microscopy image of our attempts then to ask questions like, what happens then if we take a band insulator and a mod insulator and put them right against each other? And first is a technical statement, which is to say that one can nowadays achieve structures where you can really modulate these sorts of things down to the single unit cell level. And I was visiting John Silcox in the electron microscopy group and working with David Muller at that time on this project. So what's interesting about this is, although you could say the bulk constituents are both insulators of 2 very different forms, their interfaces can often create interesting states. In this case, metallic and actually superconducting states at low temperature. I know this is not really a material-centric audience, but I just give you a brief picture of the types of things that we're doing. We're using an ultra-high vacuum version of pulse laser deposition. And so we're taking a UV laser pulse to evaporate a physical plume and deposit this very slowly and carefully on a substrate hanging upside down over here. And the key experimental technique, whether you do this by molecular beam epitaxy, laser ablation like we are, or sputtering, is that you really need to be able to see in real time and monitor these sorts of structures on an atomic scale, and that indeed is possible. The technique we're using is, while we're growing these sorts of materials, we use a grazing incidence electron beam of order 25 kiloelectron volts, i.e. a situation where the electron wavelength is of order your lattice spacing, and therefore you can see surface diffraction, and you can see a periodic brightening and darkening as associated with the roughening and smoothing of growing each layer at a time. Okay? So these are the kind of technical developments that the community has made to be able to really grow these sorts of atomically precise structures. To go back to this example then, the schematic is that we have an insulating state here, an insulating state over there. And imagine you make this very abrupt. You can easily imagine that the electrons would minimize their free energy not by making this an abrupt step, but smearing out across that interface. And in a schematic sense, what's interesting about this then gradation of charge density is if I take the phase diagram of these sorts of materials in bulk, you see going from an insulator, a superconducting state, and a metal with this characteristic feature of being increasingly correlated, effective mass enhancements until you open up this correlation gap at this Mott insulating state. So you can almost imagine that at the very least you have this entire phase diagram placed at this interface. And actually a lot of our work shows that sometimes completely new phases appear as a consequence of these boundary conditions. And so we've been studying these sorts of systems for a long time. Here's very nice work using a scanning transmission electron microscope where you use an electron beam down to atomic dimensions. If you do energy loss spectroscopy on that beam, you can not only take pictures, but you can really map out spectroscopically these sorts of charge profiles. So just to give you a typical scale in this case, that kind of relaxation length is of order a nanometer. Okay, so these are quite small dimensions at these interfaces. Yes, please. I'm sorry, this... Okay, yeah, so this is a case where we basically, this is a phase diagram as we make the solid solution from 1 to the n. So it's initially dopes like a semiconductor. It's a superconductor, I mean, so with its associated order parameter. And then you have a wide range of a metallic phase where I would say there's no, ordered state per se, but you start to see, the usual signatures of increased correlations, the effective mass starts to diverge. And here now you have an antiferromagnetic insulating state at that end. And so the point is that this would be a bulk uniform density statement. What becomes interesting is when this becomes compressed in these sorts of kind of nanoscale dimensions. Okay. So these are the kinds of research programs that we and others have been pursuing. So there are many famous examples, for example, superconductivity in the cuprates, where the onset of interesting features and phases really comes out from doping from this kind of 1 electron per site picture of a Mott insulator. Right? So if you dope holes or electrons, you find superconductivity emerging. Another example, and there are many more, here's our antiferromagnetic insulating Mott state. In this particular case, if we dope into the system, you stabilize rather an itinerant ferromagnet. And so you can imagine the game then is to imagine different configurations where we can tune this low symmetry environment to use these degrees of freedom to create low dimensional states of the system. So the dominant themes that the last 15 years a lot of our community has been working on is to take these sorts of novel correlated bulk systems. I guess the modern language is quantum materials, although I'm not sure what that means. But in any case, use these sorts of heterostructure techniques to really ask questions and make structures quite artificially where we can structure them and vary them down to atomic dimensions. Now, what's interesting about these class of oxides is that in your solid state physics textbook, I think it's fair to say every single ground state that you can find can be found in these materials, and also very importantly, found in the same kind of crystal structures such that we can assemble them one to another. So in simple summary terms, the types of questions one can then create at these sorts of heterostructures is to ask, let's take the interface between, let's say, ferroelectricity and ferromagnetism. You probably have heard of things like multiferroics, where you have 2 ferroic degrees of freedom. Or what happens when you take a superconductor and put it intimately with a magnet, what sorts of coupled or competing states can emerge. So these sorts of approaches, as well as the obvious opportunity to play games in terms of dimensional confinement of magnets, superconductors, and what have you, has been really a dominant theme and very, very active today. You know, I guess I'm kind of excited about some recent things we're doing. And so what I'd rather focus on is things that I think are getting now developed enough to be rather exciting. And so let me focus my time on telling you the last few years of effort in our group. And you could broadly say that we're trying to think of further degrees of freedom to really atomically manipulate these systems. So recognizing this is a physics colloquium, at least some of what we're going to do, and I'll just briefly touch on, comes under the rubric of soft chemistry. Okay? This is a bit of a vague term, but this is basically low temperature techniques. What I showed you in our chamber is very aggressive. You're growing at 900 degrees C, you know, really high temperature synthesis. But there's a class of chemistries and reduction reactions that really occur at something like 200 degrees C, very gentle processes, but can really make metastable phases you can't make in any other way. So this is my youngest illustrating this concept. So you've probably played this game. The idea is very similar to this, and I'll come back to this analogy. You play this game by making these sorts of stacks, and imagine you have a way to, at low energy, slide out these different intervening blocks. You can create structures that can be actually quite well ordered, but can't be accessible by any kind of high temperature synthetic approaches. So let me give you 2 examples along those lines. To introduce the first example, it's very much motivated by sitting like you in these sorts of talks. So I just told you this kind of big picture vision that we have this wonderful ability to play with all different quantum states and phases and interact them. And surely you've heard this pitch before recently. Very important and popular recent class of materials are things like graphene or layered chalcogenides, systems that you can mechanically exfoliate down to the monolayer limit and put them together. Certainly compound semiconductors, although they have, you know, many decades history, is still at the frontiers of science. So just a reminder that the first experimental example of the topological insulating state and the spin Hall effect was actually in compound semiconductor heterostructures. And there can be even more exotic ones as well. So what is the issue? The issue is, you know, that's fine. If I were a young person, I'm interested in this field, which lab do you go to, right? So for the young people, before we had iPhones, this is what you played with. I had all of these toys. They're variously good and interesting for different things, but it's very difficult to put together. And yet, many of the leading questions and opportunities in condensed matter, I would say, is more and more abstracting out the material's details. So just as one kind of important example recently, this is the first, I think, a picture from a proposal by Liang Fu and Charlie Kane when they were at UPenn, constructing heterostructures and circumstances to stabilize, you know, Majorana states, quasi-particles at their own conjugate. The point is not to go into this discussion. The point is they don't care about these details. This is a superconductor. This is a topological insulator. How do we make these components meet? So we've been playing with a funny class of membrane films. And let me tell you the inspiration. This is the first example I'm aware of. So in the 1950s, people found that if you grow things like gold or FCC metals on sodium chloride, it grows pretty well. The lattice constants are well matched. It sits one on top of each other, and you can make nice films. So sodium chloride, so these guys in 1960 had the clever idea. This is a substrate of salt, a metal film. They squirted water in the back, dissolved the backside out, and they were left with this suspended, mechanically free single crystal gold film, and played with their mechanical properties. So we've been very interested in very similar types of opportunities, and again, motivated to find different ways to connect to other material systems. And so schematically, we've been developing ways to do the same thing. So here's a fancy artist rendition. Namely, we can pick layers that we can grow with atomic precision very precisely in our clean growth chamber, but design their chemistry such that we can dissolve this layer out at room temperature. So imagine you grow this structure, you grow something complicated, put it in a beaker of water for a couple hours, and a membrane floats off. It's kind of a cool experiment. Actually, my lab is kind of a mix of physics, applied physics, and some engineering students. My most kind of a priori fundamental physics guy was doing this kind of creative chemistry. And the funny backstory that I don't have time to go into is that if you go to the hardware store and buy a bag of cement, a few % component of that is something called calcium-3 aluminum 206. So what happens in your hardware store cement, you pour water in and mix it up. This thing makes a hydrogarnet. It swells and it binds everything together. If, however, you do substitutional chemistry, you can make this orders of magnitude more soluble in water, and it grows very nicely on the types of systems that we're interested in. So imagine then you've grown this layer of a cement component, done the other things you want to do. We can make very weird geometries for these sorts of kind of ceramic materials. This is a few nanometer sheet of one of these perovskite oxides draped over a grid. Just to give you a scale, this is a 2-micron hole. So this is a very interesting geometry. You already can see some of the potential. This in bulk has the same mechanical properties as a ceramic coffee cup. But you look at this here, and it looks like kind of a sheet of fabric. It bends, it folds, you can distort it, and these are some of the things that I'd like to tell you briefly about. But the first story and the most naive question you can ask that we asked was, so how thin can you make such membranes? And keep in mind, we did this a few years ago, so a decade past the discovery of graphene and all these sorts of systems. There are lots of interesting 2D materials. So can we make this in the 2D limit? So let's try it. We've taken a particular perovskite. This is not really relevant for these details. We've made these membranes, put it on a TEM grid, and lo and behold, you have a nice lattice. You can see the ordered arrays of these atoms. And the statement would be, in summary, that when this layer, this membrane, is 5 crystallographic unit cells thick or thicker, it's all basically a nice crystalline membrane. But something strange happened when we went a little bit smaller than that. So 4 unit cells, 3 unit cells. You can see that this looks radically different. Actually, down to 2 and 1 unit cells, you can make a physically continuous membrane. But if you look at it crystallographically, you can see this is really starting to get very disordered. You can see crystalline patches and kind of getting smaller and smaller. And what was bizarre about this is we know and can show that all of these cases were nicely crystalline before we released them, this dissolving in water business. A quick example of that is that same electron diffraction experiment used to monitor their growth can probe their lattice coherence. And so you can see here basically Bragg scattering of the electron beam. So this cement component, 1 unit cell, 2 unit cells, different thicknesses of what will eventually become the membrane were all crystalline. So what's going on? Why would putting this in room temperature water do something so drastic? So the backdrop to this, as far as we understand it, really comes to this long-standing discussion of the question of can low-dimensional crystals exist? So many early discussions, these are just a few highlighted here, led up to essentially what we know as the Merman-Wagner theorem. That is to say that in systems that have 2 dimensions or less, you cannot break any continuous symmetry at finite temperature. Right? So this is going through the late 60s. And of course, the next important conceptual step in this kind of train of thinking was to say, yes, that's formally true, but actually at finite temperatures, you can have pseudo-ordered phases. Namely, you can have lattices stabilized by topological defects. Right? So the original work of Berezynski, Koslas was looking at model spin systems where the stabilizing defect would be vortices, right? Vortex-anti-vortex pairs. In the specific case of crystallinity, this is very much a crystallographic defect, as illustrated here. So this has actually been something that has long been sought after. And to make a long story short, it's very difficult to look for and examine this melting transition just in terms of the kind of energy scales associated with crystallinity, at least for typical kind of room temperature observations. So I'm already leading you towards thinking that this might be the issue. I thought it was actually funny. Somewhere on a plane years ago, I saw this. I don't know if you guys read the New Yorker out here, but this was a long general audience article discussing graphene. Okay, and it was interesting that these famous people were complaining about referee reports, like we all do. And their initial paper discussing this exfoliation of graphene was rejected because essentially referees say, everybody knows by Merman-Wagner theorem, you can't have a 2D crystal, so what are you talking about? Now, I'd like to connect back to this in a moment, but let me tell you then a scenario that we have been developing to understand this transition, and namely that the cartoon diagram of this Koslas transition is that at t equals 0, I can have formal long-range order. And below some characteristic temperature scale, I have a quasi-crystalline phase stabilized by paired dislocations. And I can define a melting temperature of the system as a scale in which we have an exponential increase or proliferation and unbinding of these sorts of defects. So to make an experimental connection to this picture, what I'm taking here is from those sorts of electron microscopy images, a measurement of the crystalline coherence length. So how long do you have to go before you lose crystalline coherence? And what you see as a function of the thickness of the membrane, what your eyes told you before, that above 2 nanometers or so, it was quite crystalline, but then we exponentially lose crystalline order. Right? So we can pull this out from, say, autocorrelation functions of this. So this and other experimental measurements essentially showed us that this is exactly mapping nicely to this BKT melting scenario with one weird feature, which is that the effective temperature scale of this transition was on the scale of an electron volt or 2. And that's very strange for something we did in room temperature water. So the basic idea here is that even though this seems gentle, the process of dissolving this layer, right, playing these Jenga games and pulling this thing off, is actually something that occurs on that several eV scale. Namely, we have ionic bonds that we're breaking as we solvate this system, and that bond strength is of that order, typically a volt or 2 per unit cell. And if our conjecture is correct, then the fluctuation energy driving this kind of melting transition is really coming from not the room temperature or KT, KBT, but it's really coming from breaking these sorts of bonds. So realize I'm actually going a bit slowly, so let me skip the details. And basically, the idea is that in this 2D regime, the energy of one of these topological defects scales linearly with the thickness of the membrane. And so I can tune that in an experimental fashion. And so rather than thinking about something that's occurring at 25 millielectron volts, say at room temperature, what we're really doing is looking at this kind of electron volt scale. And by varying the thickness of these membranes, we can cross this BKT melting line in a very different way. And sure enough, if you do the appropriate scaling analysis, the system looks very much and with the right exponents for this kind of topological melting transition. So this was quite satisfying. At least it gives us a phenomenological handle of what we saw. And if I try to connect back to things like graphene, things you also know that can be very quasi-crystalline on very long length scales, you can see that if I take systems where I generate a 2D lattice by exfoliating or removing from a 3D host, if I have a situation like graphene, which is so anisotropic, meaning the in-plane bonding and crystalline energies are very large compared to the out-of-plane, right? That anisotropy exceeds 100. It's a formally fair statement to say that this is not truly long-range ordered at room temperature, but this is a kind of argument where that scale is the size of the Earth or something, right? But if we go to systems, and now there are more and more examples that we and others have been examining, to the case where we're isolating systems where that kind of crystalline cohesion is more isotropic, then we can actually access and observe this transition, as I've shown you by these sorts of electron microscopy images before. So that's both useful. It tells us what to do if we want to now bring this boundary down, how to manage that interface energy. And it's also something rather interesting. So one of the things that, for example, we're interested in is what happens when this is not just a structural material at the level of our discussion. What happens when this is a magnet or a superconductor? How can we play with and probe this topological crystalline defect in the context of other order parameters of the system? What is the conventional ending time? Just to make sure. Yeah, but anyway, let's agree on a time. So I don't 15. Okay. Okay. Maybe in the interest of time, then I'll just flash one result here, but I would like to introduce something new at the end. So a lot of the opportunities that we're playing with in these sorts of very unusual geometries really has to do with their nanomechanical manipulation of these systems. You can make very nice, fairly high-Q mechanical resonators, right? Little drum head mode resonators, and ask how that couples to other states of the system, magnetism, superconductivity, and what have you. And you can also play games in terms of stretching and straining them to very extreme states. So just to give you a quick pass through one of the aspects that we've been studying, this is a case where we've made one of these membrane films. It's a few nanometers thick. We've engineered kind of a structure where we put this on a fleximer polymer, and we can stretch this membrane, and quite dramatically. We can exceed kind of 10% order scales in these sorts of systems. So why that's interesting is that if you remember back to the other phase diagram I briefly showed you, cases where out of a Mott insulator, we dope this and what's born is an itinerant ferromagnetic metal. These are now situations where by straining and stretching these membranes, we can really shift and change the phase diagram in a very simple and direct way. So this is an example where we take a metal insulator transition and ferromagnetic transition, and we can strain, drive the system. So again, let me skip the details, but say that this is really now kind of almost what a theorist would do. A theorist might calculate, for example, what is the phase diagram and instabilities in terms of the electronic bandwidth or other scales, and this is something we can directly manipulate. And so in this particular case, we can understand the competition between these different states in terms of a very microscopic picture in collaboration with friends doing electronic structure calculations, where the simple message is in one side, an itinerant magnet wins. If I pull this apart, the lattice becomes wider and wider. The electronic bandwidth and overlap gets smaller and smaller. You can imagine a localized antiferromagnetic insulator wins. There's quite a remarkable set of new tools that we now have to kind of strain manipulate. We can apply different symmetry strain fields and ask, for example, what happens in a cuprate superconducting membrane or a ferroelectric membrane. So what I wanted to make sure I told you about, although it's probably still at early stages, is a second example of this kind of soft chemistry idea. And let me introduce to you the broad topic, which is kind of very soon after the discovery of superconductivity in cuprates. There's been lots of theoretical suggestions of looking for new superconducting systems via analogies to this material. So let me first just remind you the very first experimental discovery of Bednorz-Mueller was to say a very weird place to look at that time for superconductivity, these sorts of, weakly conducting brittle oxide systems nevertheless showed a superconducting transition. Now, this is a very complex subject, more than 100,000 papers later, let's say, but the key ingredients that we do know is uniform through a whole host of these sorts of cuprates is that it has two common ingredients. It is composed of copper oxide planes. So this is the important electronic states of the system. It again comes out of an antiferromagnetic insulator that by doping the system, you induce superconductivity. And finally, that when we dope, for example, holes in this system, that the types of states that you're dealing with are these sorts of so-called Zhang-Rai singlets. So you have these states that are composed of copper D hybridized with oxygen 2p orbitals. Okay, so you can think of this as your entity. And as I'll return to, this kind of structure deeply connects to the fact that without doping, it's a very high temperature scale magnet. And this is considered really the background or the parent reference state out of which superconductivity emerges. So a decades-old question, it's probably earlier than this, but one early reference I see from these guys was, if we've now learned that there's such a thing as superconductivity in cuprates, can I make other analogs to that? Okay. So one example would be, as we'll pursue, nickel is next to copper on the periodic table. If I could make this system, nickel 1+ would have the same configuration as copper 2+. Again, it's a system with 9d electrons. You can think about the 5d states. You fill up, down, and you'll be left with one free spin. Right? So this is the moment that is antiferromagnetically ordering. So why, then, if this is such an old and conventional idea, was this not obvious or successful so far? Well, one of the things, I take a picture here of a more chemistry-oriented periodic table. In order for this to be true, I need to make something that is very unusual, very unstable conventionally. I need to make nickel 1+, which you can see here is the kind of the popular oxidation states of compounds of this material. You see 2, you see 3, you don't see 1. Okay, so that's what was the challenge. But again, there's these very kind of fascinating, at least for, I think, our community, underappreciated and utilized techniques that can really create very different structures than conventionally synthesized. So there's a few efforts over the last few decades that developed ways to, for example, do exactly this Jenga process. So you can literally imagine there was a column of oxygen here, pull that out. Another column of oxygen. So you can actually transform stable known materials that we can easily grow in both bulk and thin film form, and we can stabilize something that might look like an analog to the parent compound of cuprates. So indeed, Denver Lee was able to do this. And so skipping the materials details, what's also very useful about being in our thin film world is that if we grow these sorts of nickelates on a substrate, not only can we make this transformation, we can force it to be crystallographically oriented, so we can make nice single crystal thin films where we've made this transformation. So what we look at, for example, is first the Perovskite phase. This actually is a classic Mott metal insulator transition. Has 7 d electrons. This is the one free electron. And what you're seeing here is the low temperature phase. We have an antiferromagnetic insulator as a stable ground state. But if we then make this chemical transformation, we can see that this has quite a different feature. And then motivated by the analogy to the cuprates that we should dope of order 20% holes in this system, what we found is that indeed we can find a superconducting infinite layer phase that's analogous to the cuprates. So a slide or two, maybe a little bit for the specialist, if we look at the superconducting properties, it looks actually like already a fairly robust superconductor. We can have critical current densities approaching 200 kiloamps per centimeter squared. As a first proxy to kind of important length scales of the problem, if we look at how superconductivity is suppressed by magnetic field, you can extrapolate a Ginzburg-Landau coherence length. So that is the characteristic, let's say, length scale associated with pairs of electrons in the system. It's about 3 nanometers. And by looking at the magnetic response, we can have a first order statement that the London penetration depth, the length scale over which you screen a magnetic field in the diamagnetic responses of the order of micron or 2. So it looks like clearly in a type 2 superconductor regime. So this is the first report. This is the first time I've ever talked about it. So this is very early days, but at least to frame some of the things we're thinking about. A very central question is, to what extent this analogy complete, and therefore perhaps uninteresting, is having 9 d electrons, whether it came from nickel or copper, the same or different? Now, one of the things that seems very relevant for these types of phase diagrams is that it's considered broadly a signature of unconventional superconductivity in the sense that it's in the vicinity of something quite different, an important ordered phase. Okay? And just to remind you that if I think about superconductivity in conventional metals using electron-phonon interactions, the idea in schematics is that if I have electrons moving much faster than the lattice, you can imagine electrons zipping through and polarizing the lattice, that this lattice deformation or phonon can mediate an effective attractive interaction between 2 different electrons. Okay? So this is a case where superconductivity emerges by electron-phonon coupling. And the statement would be that this proximity of magnetism and the very high scale of transition temperatures in cuprates has long been considered indications that perhaps spin fluctuations of this antiferromagnetic state mediate superconducting coupling here. So think about, say, effectively a magnon here rather than a phonon. So is this also relevant for the nickelates? Again, it's early days. But in the literature, at least, the undoped parent compound, 2 of them have been studied by groups in Europe. No magnetic order is seen down to low temperatures. Right? So it seems very, very different from what we know about the cuprates, where, again, you have nail temperatures on the scale of room temperature, 300 Kelvin or so. Here, that seems to be very different. And we've been studying also things like magnetic excitations using inelastic X-ray scattering techniques. And at least we can say that we don't see any magnetic excitation features in this system, where it was very clearly seen up to 200-300 MeV in cuprate systems. So this is actually an interesting dilemma that perhaps as we understand the system better, the analogy or the differences between cuprates may be illuminating, but at least this reference antiferromagnetic state seems very different in this compound. And part of the way you can understand that, let me give one slightly specialized slide here, and I'll conclude, is that actually 9 electrons in a cuprate is quite different from 9 electrons in a nickelate. And one of the ways you can see this is in terms of their orbital energy alignments. So I've drawn this picture before, namely that if I dope holes into this antiferromagnetic insulator, you create states that are predominantly hybridization between copper dx squared minus y squared orbital and this oxygen 2p band. And you can kind of imagine, or this so-called singlet formation is very much consistent with a situation where you have strong antiferromagnetic exchange between sites that may be still quite persistent upon the doping of mobile holes. By virtue of nickel being 1 over on the periodic table and 1 less oxidation state, the hierarchy of energy scales is very, very different. Namely, that when we dope holes in this system, as far as we can see, this is recent spectroscopic work led by Weicheng Li and lots of collaborators locally. This is a very different state. Namely, we have hybridization between the nickel D state and the 5Ds of lanthanum or neodymium or these sorts of systems. So in fact, if you look at an electronic structure calculation or a projection of this, what you see in this case is something that looks very, on the one hand, reminiscent of this same story here, but we seem to have also a second band, and this is really coming from this kind of lanthanum or neodymium 5D character. And so at least one of the ideas being kicked around by some of my theory colleagues here is that this might be actually a very interesting analog to the so-called Kondo or Anderson lattice model, that you have this narrow upper Hubbard band of these nickel 3D states hybridizing with this broad band of 5D. So Zanen was saying maybe this is a first example of an oxidic heavy fermion type system. So it's just an idea, but some of the things that we've been thinking about. So the final statement I just introduced briefly is that this kind of structural motif, of which one of them we find to be superconducting, is part of a whole different family of layered oxides that chemists have been studying and discovering over the years. And so this is just a speculation, but there is the tantalizing possibility that much like the cuprates or the iron nictide superconductors discussed over the last 10 years or so, that there might be a wide family of superconductors in this class of materials with, again, this common theme of having a two-dimensional intrinsic structure. So it's to be seen, but it's quite exciting for us. And we're working hard on that direction. So let me just close here. And I just wanted to give you kind of an introduction to our field. And first, I showed you a little bit about kind of the main activities over the last 15 years or so of our community trying to develop increasingly sophisticated structures and measurements of semiconductor heterostructure analogs using these sorts of strongly correlated materials. And I tried to spend then the majority of the time telling you about two kind of promising new directions. One is to take these sorts of heterostructures, but then further play with them in membrane form. I just gave you a taste. Actually, there's lots going on, not just in our lab, but around the world, where you can really start to ask interesting new questions. For example, take a superconductor. I bend it. Can interesting things happen when you break inversion symmetry artificially in this system? This is really mechanically quite an interesting degree of freedom. You start to see lots of possibilities. that I think will grow going forward. And finally, fairly recent work where we found that actually that using these sorts of novel chemistry approaches, we can actually stabilize a new family, hopefully, of superconductors in the nickelates. And it raises a lot of interesting questions that both either reinforce or question what we think is the dominant way to think about superconductivity in cuprates. So hopefully this will be something that is illuminating in the years to come. So yeah, with that, let me thank you for your time.
Thanks a lot.
Yeah. It's something like 9 to 15 Kelvin. Yeah. 9 to 15 Kelvin. Yeah. Okay. Yeah, that's easy to answer. No, I know nothing. I mean, basically, in some sense, this is what we know. Hmm? Yeah, so I've skipped some of the details. So basically, we at present cannot prepare a clean surface in order to do ARPAS. That would be the first statement. And as some of you may know also, 10 Kelvin is kind of borderline scale to see a spectroscopic gap. There's been, I don't know, this paper's been out for a month or two, and there's more than a dozen theory scenarios. I think the summary statement is even with the specifics of this electronic structure, the kind of typical RPA type of discussion seems to say that x squared minus y squared would be the dominant pairing, even with this other state or band in the problem. Yeah, so it's not the only thing. NMR is also hard. So I don't know. I might have stuck this somewhere. Yeah. So happy to talk more in the details. Our constraint is that we can make this reasonably clean and reasonably single phase down to, up to about a 10 nanometer thick film. So it's really a trick of playing games here. And I met your local NMR guy, and I've talked to others. This is a terrible volume and geometry to do anything with. So there are things that we should do and try, and we are thinking, but you know, as I said, these are all very good questions. We need to work hard. Yeah. Yeah. Sure. Oh, yes. Okay, I understand. This business? Okay. Okay. So yeah, I went a little bit quickly in the interest. Um, so the basic story of this is that you know, for this crystalline story, the BKT transition temperature or energy scale corresponds to one lone defect. Yeah. And so the point is that the knob we have is that in the 2D regime, the thickness of the membrane directly controls then the energy cost of that defect. And what I was trying to schematically show you here is that we haven't done the conventional temperature-dependent path of going from low temperature up past this melting scale. What we're saying is that we see a snapshot that seems to be very consistent with having made an excursion at this, you know, electron volt per site type of scale. So it's as if we took a snapshot or quench from this very high energy scale. So that was the one kind of strange, obvious feature that would be, you know, not obvious, at least in our thinking, for something that came out by putting something in room temperature water. But then the scenario we have is that actually this solvation, dissolving this layer, is really microscopically picking out these, you know, I have to dissolve these bonds. And that is at least our scenario. I mean, it's not necessarily a fact. Now, there's a, I should give you a few caveats I don't have readily at hand. There's some incomplete signs of things like a little bit of this orientational order that you might expect in that. We haven't studied it in great detail. The one thing that may be quite different from a conventional BKT transition in temperature is that there's spatial. Okay, so what happens? I'm dissolving this layer out. So you can kind of imagine the zone where we've dissolved this layer out. This is not exactly the same thing as having something at high temperature and quenching it down. And so there could be some consequence associated with the fact that we have essentially this this fluctuation energy, not in some uniform way, but in some sort of propagating front. So we're thinking a little bit about how to consider that. That could be quite qualitatively different, I should say.
Before the end, let me clarify that all what I was talking about in introduction about the invention of what is called conceptuality has nothing to do with the topic. Always the past and
Oh.
opportunity to present new direction how to make.
Okay, well, thank you.
Okay, thanks again.
Okay, thank you.